Okay, next we start to take a look at quantitative examples of gravitational potential energy in this Newtonian form. Let's immediately begin with the following. Copy down the example into your notes. Okay, an object is thrown upwards from the Earth's surface with a speed of 10 kilometers per second. What is the maximum height reached by the object? Ignore the Earth's rotation. This will be part A of the problem. And then part B of the problem, in just a few minutes, we'll make a comparison by comparing the values that we calculate by thinking of gravitational potential energy as mgh. But we'll get to that later in part B. Okay, for now, however, in part A, we have the following. Okay, so here's the Earth like so, and then consider once again the origin to be the center of the Earth. Right here is the mass of the Earth. Now, because the origin is the center of the Earth, as the Earth rotates, if you were at the surface of the Earth, you would then therefore have kinetic energy with respect to the origin, with respect to the Earth's axis of rotation. This is, of course, taken into account whenever we launch projectiles into space, for example. However, we're going to ignore that detail here. A little bit later on, I'll give you a qualitative understanding as to what happens if we do include the Earth's rotation. But for now, the Earth is not rotating, and then therefore right here is our object of mass m, and we throw it upwards with an initial speed v0 of 10 kilometers per second. Now, 10 kilometers per second is 10,000 meters per second. Okay, and then the object rises to some height above the ground. Here's the object of mass m once again, and its final speed v here is equal to 0 for an instant prior to falling just back down to the surface of the Earth. Okay, the unknown in this calculation is going to be this distance r here, like so on the diagram. That's the distance that the object rises with respect to the center of the Earth. Once we calculate what r is, then we'll just subtract out the radius of the Earth to obtain the altitude above the ground. Okay, now we have some known numbers here in a problem such as this. These are numbers that you were introduced to, for example, in the unit on gravitation. We have capital G, of course, the universal gravitational constant, which is the following. Okay, and then we're also, of course, going to need the mass of the Earth in this problem. This is 6 times 10 to the 24 kilograms. And then a little bit later on, we're also going to need the radius of the Earth as well. That's 6,400 kilometers. That's 6.4 times 10 to the 6 meters, like so. Okay, and now we set up our conservation of energy expression, and in doing so, we do have to write gravitational potential energy in its Newtonian form. The general expression is, once again, the following, as derived in the previous lecture. So, okay, so let's just go ahead and set up our conservation of energy expression and just fill in all of our terms. So 0 equals delta K plus delta U. So first of all, change in kinetic energy. Our final kinetic energy is 0. The initial depends upon V0. So final minus initial looks like this. Okay, and now we get to this new term, the change in gravitational potential energy. Our final gravitational potential energy depends upon the unknown distance r, and then therefore we write this in the following way. Okay, notice the negative sign. Okay, and then minus the initial gravitational potential energy. The initial gravitational potential energy is not 0 because keep in mind that the origin is the center of the Earth. So then therefore we of course need this distance here, which is the radius of the Earth. Therefore the initial gravitational potential energy looks like this. Watch your negative signs. So final minus initial. Like so, and now we just go through the math here and we solve for small r. So let's go ahead and do the math. What I have to do first of all here in this term is cancel out these negative signs like so. And then let's go ahead and take this term here and then move it to the other side of the expression. I'll do that here. Once again, just be careful of your negative signs. Like so. And now what I'm going to do is basically just cross multiply. Actually, the next thing I'll do is cancel out the mass of the object. So let's just go ahead and get rid of that at this point. And now I'm going to go ahead and cross multiply and solve for small r. So take the small r and move it up there to the numerator on the right-hand side. Take all of this stuff here and move it down to the denominator on the other side. So after you move things around, let's see, did I get this correct here? I'm putting it in brackets down here like so. There we go. And now we plug in all of our numbers. Okay, so doing so, hang on a second, I need to get my calculator. Okay, so first of all, I'm going to do the brackets down here in the denominator. So -1/2 and then times 10,000 squared. and then plus g times the mass of the Earth divided by the radius of the Earth. Okay, put all of that up into the numerator and then multiply by the numerator. So times g times the mass of the Earth. Okay, so after all of that, rounding it off a little bit here, I end up with 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. It's about 3.2 times 10 to the 7th meters. This, however, is not quite the answer. The answer, of course, to find the altitude above the ground, which is usually called h once again, is to take this value and subtract out from it the radius of the Earth. Okay, so let's go ahead and do that. So the altitude h is small r minus big R. That is the radius of the Earth, so let's subtract out the following. Okay, and that comes out to be about 2.55 or so. Once again, let's make sure I get the exponent here correct. 1, 2, 3, 4, 5, 6, 7 times 10 to the 7th meters, like so. So if you take an object and you throw it straight up with an initial speed of 10 kilometers per second, ignoring the Earth's rotation, it rises to a height above the ground of roughly 26,000 kilometers. Okay, now let's make a comparison in part B. Let me go ahead and move my file. So in part B it says, how would the answer change if instead the gravitational force was treated as a constant? In other words, we think of gravity as just mg, and then therefore gravitational potential energy would be mgh. So if we use mgh as our gravitational potential energy and then calculate what h is equal to, do you expect it to be equal to the quantity that we found here, less than, or greater than? It should be less than. And the reason for that is because remember in reality that gravity gets weaker with distance. So then therefore as the object rises above the ground, the gravitational force exerted upon it due to the Earth decreases, and then therefore it should rise to a greater height in reality than it would if we then did the approximation that is being asked for in part B. So let's go ahead and do part B and then we'll compare it to this value here. Okay, so in part B we would just kind of set it up like so. So here's the ground. Okay, we treat the ground as the origin in this calculation. Here's our object thrown upwards with V naught, once again equal to 10,000 meters per second. It then ends up at rest up here somewhere like so, a distance h above the ground. And now we just set up our conservation of energy expression once again. So 0 equals delta K plus delta U. Okay, so we start filling in our terms now. Okay, first of all, change in kinetic energy. So our final kinetic energy is 0. We end up at rest, and then minus the initial, like so. And then change in gravitational potential energy. Final value of mgh minus the initial value of 0. Like so. And now we just solve for h. So let's move this term to the other side. Like so. Let's now go ahead and cancel out the mass of the object at this point. And then once again, we're solving for h here, so just divide the g to the other side. That then gives us the following, and now let's plug it in and see what we obtain. Okay, so in the numerator, I have 10,000 squared, and then divided by 2 times g. And this ends up being 1, 2, 3, 4, 5, 6. It ends up only being 5.1 times 10 to the 6th meters, like so, considerably less than the actual value. Once again, the actual value is as large as it is because the force of gravity gets weaker with distance. So now kind of summarize this problem in the following way. You take an object and you throw it upwards as we're doing here in this example. It then rises to some height and then eventually falls back to the Earth. Let's say that I throw it faster, however, than 10 kilometers per second. This then means that ultimately it's going to rise to a greater height above the Earth prior to falling back down to the ground. However, if I take the object and I throw it hard enough, it will literally never fall back down to the ground. It will have gravitationally escaped from the Earth. What we're going to do in the next example is calculate the initial velocity that the object would have to have such that it would literally never fall back down to the ground once again. This unknown initial velocity is referred to as the Earth's escape velocity. So let me go ahead and move to the next example. Okay, let me also do some erasing. Okay, we're going to once again need these values here for this next example, so I'll go ahead and keep them here. It now says, what is the Earth's escape velocity? Once again, ignore the Earth's rotation. Okay, so then therefore we have the following. This is actually an easier example than the one that we just completed. So right here is the Earth once again, right here is the origin. We have the mass of the Earth like so. And then we throw the object of mass m upwards with some unknown initial velocity. This is referred to as v escape. Okay, now, where is the final position in this problem? Think of it this way. Where do you have to be such that the force of gravity exerted upon you is equal to 0, and then therefore you will never fall back down to the ground? You have to be infinitely far away. So then therefore the escape velocity will occur when the object of mass m ends up infinitely far away from the Earth with a speed of 0. So right here is our final position in the problem, and r is equal to infinity, and our speed is equal to 0 at that point. So we now set up a conservation of energy expression where we now treat our final position as infinitely far away from the Earth with a speed of 0. Okay, so now here is our conservation of energy expression, like so. And then once again, we just start filling in our terms. So first of all, the change in kinetic energy. So our final kinetic energy is 0. Okay, and then minus the initial with the unknown v escape, like so. Okay, now changes in gravitational potential energy. My final gravitational potential energy will be 0 because we end up at r is equal to infinity, like so. And then be careful here, minus the initial value at the surface of the Earth, where once again the distance that we need here is the radius of the Earth, because the center of the Earth, remember, is considered to be the origin. So final minus initial, like so. Once again, just be careful of your negative signs. Okay, here in this second term, the negative signs cancel out, like so. Okay, let's go ahead and move this term here to the other side. Like so. Throw away all of my zeros here as I do. And now let's just go ahead and do the remainder of the algebra here to solve for v escape. So at this point, I'll go ahead and cancel out the mass m of the object, cross multiply by 2, and then take the square root like so. Oops, g times the mass of the Earth. There we go. And then divided by the radius of the Earth. Like so. This right here is a very well-known expression when it comes to astronautical engineering. Launching spacecraft from the surface of the Earth, for example, to say explore the solar system. After I complete the problem in just a moment, I'll give you a qualitative understanding of what is necessary, for example, to send human beings to Mars. It's not like Star Trek, it's not like Star Wars, as you'll see. Okay, let me go ahead and finish the problem, however, before I get to that. All right, so the square root of 2 times g, like so, times the mass of the Earth, like so, divided by the radius of the Earth, like so. And after all is said and done, you end up with about 11,183 meters per second, just under 11.2 kilometers per second. This is once again a well-known number when it comes to astronautical engineering. So think of the problem like this. Like in the previous example, you take the object and throw it upwards at an initial speed of 10 kilometers per second, and it rises to the height that we calculated above the surface of the Earth prior to falling back down to the ground. Throw it a little harder, it ends up at a greater height above the ground before eventually falling back down. However, if you throw the object upwards with this speed, it will literally never fall back to the Earth because mathematically it ends up infinitely far away with a speed of 0. If it's infinitely far away, then the force of gravity exerted upon it is equal to 0. If you throw the object, however, harder than this value, then ultimately the object will end up at infinity. It will still have gravitationally escaped from the Earth, but it will do so with some final speed. And then at that point, it would just obey the law of inertia. It would move at a constant speed in a straight line forever. Once again, it will have gravitationally escaped from the Earth. Okay, so now keeping these types of calculations in mind, let me give you a qualitative description of what is necessary to send a spacecraft, for example, say from the Earth to Mars. As I said earlier, it's not like Star Trek, it's not like Star Wars. When it comes to chemical rocketry, there is kind of like a vicious circle, if you will, that's a problem that is extremely difficult to overcome. The problem goes like this. Let's say you want to go from the Earth to Mars, and you want to do so as quickly as possible. So then therefore you need to use a lot of energy to do so. In order to obtain enough energy to do so, you need a lot of rocket fuel, which then therefore increases the mass of your spacecraft. So if you increase the mass of your spacecraft, this then means that you're going to need more energy. So you're going to need more rocket fuel. So then therefore you increase the mass of your spacecraft, which then means that you're going to need more energy, and so on and so on and so on. So there's this vicious circle, if you will, when it comes to expending energy to go quickly, say, from one location to the other in the solar system. So then therefore we try to do this, say send a spacecraft from the Earth to Mars with as little energy as possible. Therefore we are stuck. We have to do it in the following way. Okay, let me do some erasing here. All right, so this is just a qualitative description. Let me write it here as such. Qualitative description of sending a spacecraft from the Earth to Mars. A manned mission to Mars will take place sometime in the next decade or so. It will at least be attempted. It will be an extraordinary feat of engineering if it is, in fact, successful. Okay, so let's say you're going to send a spacecraft from the Earth to Mars. Here's what we're up against. Okay, let's say right here is Mars's orbit about the Sun. Let's say right here is the Earth's orbit about the Sun. Let's say right here is the Sun. Okay, now let me go ahead and position the Earth here on this diagram, like so. And let's say the Earth, as it's orbiting the Sun, is doing so counterclockwise on the diagram. Mars is then therefore doing the same thing, like so. Okay, as the Earth's orbiting around the Sun counterclockwise on my diagram, it's also rotating on its axis counterclockwise as well. So then therefore the Earth's rotation looks like this. Okay, and now you want to throw your spacecraft from the Earth to Mars, and you want to do so with as little energy as possible. Therefore, you need as little rocket fuel as possible. So how do you do this? Well, the first thing that you take advantage of is the Earth's rotation. As I mentioned earlier, because the origin in this calculation is the center of the Earth, at the surface of the Earth, as the Earth rotates, you already have some kinetic energy. You want to take that into account. Now, the Earth rotates from west to east. So then therefore what you want to do is you want to throw your spacecraft in the direction of the rotation. You want to throw it out towards the east. You also want to do this as close to the equator as possible. So then therefore if you are as close to the equator as possible relative to the Earth's axis of rotation, you have the greatest amount of speed. That's why the United States has two launch facilities here in the country, one on the west coast and one on the east coast, and they are located basically as far south as possible. So here on the west coast, Vandenberg Air Force Base near Santa Barbara is used as a launch facility. It's basically as far south as you can be in the country while on the west coast. But then over on the east coast in southern Florida, of course, at Cape Canaveral, that's where we have our main launch facility. And then in each case, what you do is you throw the object out towards the east because that's the direction of the Earth's rotation. So if the Earth is rotating on my diagram here in this counterclockwise fashion, this then means that you basically want to throw the spacecraft from either this time of day right here to about this time of day right here. In other words, there is a launch window in terms of the time of day where you can actually throw your spacecraft. So what times of day did I indicate here on this diagram? Well, this right here is pretty obviously midnight, and then therefore this right here is sunrise. So then therefore basically what you want to do is you want to throw your spacecraft out towards the east as early in the morning as possible because you're rotating in that direction. And then usually you expend all of your rocket fuel after just a few minutes, maybe 10 minutes or so of firing your engine, and then the engine shuts off. And then what happens at that point? Well, the spacecraft then just orbits the sun, and it does so in an elliptical orbit. It obeys Kepler's first law of planetary motion. This is, of course, assuming that you have expended enough rocket fuel such that you have gravitationally escaped from the Earth. So then, therefore, your spacecraft does this. Like so. It obeys Kepler's first law of planetary motion. It orbits the sun in an ellipse. Right here at the position of the Earth will be its perihelion position. Right here at the location of Mars, that will be its aphelion position. Now, besides being able to launch the spacecraft at a specific time of day, Mars itself has to be in the correct position in its orbit for you to be able to do this. So when we launch the spacecraft from the Earth to Mars like so, at the moment of launch, basically Mars has to be right here roughly on the diagram in its orbit. So in the time necessary for the spacecraft to cruise from here to here, Mars then moves from here to here in its orbit, and the two objects then arrive at the same location together like so. So you have to have the planets basically lined up correctly in order for you to throw your spacecraft from the Earth to Mars. Now, the total amount of time that is necessary to cruise from the Earth to Mars is 9 months. There is no way around this when you use the least amount of energy possible to do this. This type of a transfer, by the way, as it's referred to, transferring using the least amount of energy possible to go from, for example, the Earth to Mars, is referred to as a Hohmann transfer. So in a Hohmann transfer, you're using the least amount of energy possible to go from one location to the other. I highly recommend, by the way, that if you haven't already done so, that you watch the movie, The Martian. If you watch The Martian, you pay attention to the dialogue when they're trying to rescue Matt Damon's character on the surface of Mars. They talk about sending him supplies by using a Hohmann transfer. That would take 9 months to go from here to here. And then let's say that you are going to send a manned crew to Mars. Your total mission time is about 36 months. It's 3 years. And the reason for that is because it takes 9 months to get there, and then you have to stay there for a year and a half. You have to stay there for a year and a half until the planets line up again, and then you launch from Mars back down to the Earth like so, and it's 9 months back. So 9 months to get there, 18 months to stay there, and then 9 months back. It's at a minimum a 3-year mission for that reason. It's not like going to the moon, which is relatively easy and is just a couple of days away. Going to Mars is a whole nother ball game. Right now, the odds of this happening successfully, where the entire crew makes it back alive, from what I've read right now on the first attempt, it's probably considered to be about maybe 2 out of 3, something like that. Because the hazards that the people would encounter are enormous. Number one, you basically have to take an entire miniaturized version of the Earth's biosphere with you. You basically have to recycle everything as much as you can: food, air, and water. In addition to that, you're at the mercy of the solar wind during the transfers. That is from here to here, and then back once again from here to here. The amount of radiation dose that the astronauts would get would be probably large enough to kill them if there was a solar storm that occurred during the journey. Probably the lifespans of the astronauts themselves will be shortened by making the journey, because probably later on in life, even if they do successfully make it back to the Earth, their lives would be shortened perhaps by cancers that would develop due to their radiation exposure. And then you have to cram a relatively small amount of people into a small space, and you have to keep them alive for 3 years in this manner. And how do you keep the crew from going crazy as a result of being crammed together under extremely stressful conditions? So right now, because of these hazards and more, which I'm just briefly summarizing here, right now it's considered to be 2 out of 3 on the first attempt that everybody actually makes it back alive. But it will be attempted soon, and it has to be done so soon. The reason why is because we do have to expand out into the solar system and exploit the resources that are there, because we are slowly draining the resources that we have available to us here on this planet, and this has then led to all of the problems that we see today: overpopulation, climate change, etc. Okay, that concludes this lecture.